I hope you're awake. I got a fun logic problem for you to start out with. All right. Buckle up. It's not hard. It's actually, we're going to reduce this to just thinking about what transformation we need to make. So we're going to write a synthesis that will allow us to go from an alcohol to a nitrile. We don't know how to do that directly, so we're going to need more than one step. Furthermore, pay attention to stereochemistry, wedge to wedge. And in fact, what I'm going to do just to simplify this is let myself think about the fact that all I need to realize is that, yes, I am doing alcohol reactions, so I'm going to draw in my alcohol. But I'm really thinking about how I can get a nucleophile, because the only way I know how to put a nitrile on is with an SN2. So I'm going to put in a nucleophile there. It's a strong nucleophile. But for it to have come from an SN2, it would have done inversion. So how do we have a retention while still doing something we know only happens with SN2, right? So comes from CN minus SN2 nuc. How about double inversion to keep retention? Two negatives make a positive. So two of the same cancels them out to make it back to the original, right? So if I invert SN2, then SN2 again, I go back to the original inversion, or excuse me, original configuration. So in other words, if I think backwards, in order to have gotten to that nitrile, I have a different new group on the dash. And that could have come from there. So let's fill this in. Let's go forward now. What can I do to get something that's a nuc that's also a leaving group? So whatever new group I bring in has to also serve as a leaving group. Had to do an SN2. What alcohol reactions have we covered that can do an SN2 on an alcohol to introduce a leaving group? How about PBr3? That's going to be a favorite, actually. We really like PBr3. Oh, I'm going to make sure I'm really careful here. Bromine here, H there. Inversion. Oh, thank goodness, because we know that bromine's a good leaving group. We could do our old-fashioned SN2 now with something like NaCN, right? So double SN2. Equals double inversion. And since there's only two states to choose from, that equals net retention of configuration. How about if we want to actually keep the inversion, yet we have a problem because we can't get here directly, so we need more than one step. But if we do two steps, we end up with net retention. If we do two SN2s, that is. Could we do something that's not an SN2 that keeps our wedge for the first step? How about something that would turn OH into a good leaving group, but keep it there? We don't want acid, because if we turn it into water, then we're getting into carbocation territory. So this is where O with something attached that's a good leaving group, like when we're done, like tosylate, right? OTS comes in handy. So tosyl chloride. You know what I'm going to do is I'm going to do a retro first, because I think that would help. Let's do a retro like I did on the other one. So in other words, my reasoning is before I get there, I need to have my leaving group on a wedge, right? Because we know the only way to make the nitrile is with an NaCN SN2. So what could have come, that would get me back there. Is there a way to go from alcohol to leaving group that stays on a wedge? And so yes, that would be our 1 tosyl chloride. Pyridine is our first step, or mesyl chloride. So let's write that full synthesis out in detail. And actually, I'm going to show you how to write them as your solution manual will often write them. The full synthesis, all steps shown, but over one arrow. So step 1 was TSCl, PYR. Step 2 was to get the tosylate that kept the retention, right? So we end up with this, OTS. Because to make the tosylate, we didn't touch that carbon. We only messed with the oxygen. The oxygen stayed on the wedge the whole time. All right, step 2 was NaCN. So this was an SN2, and the top one was not. It was simply replacing the H with a TS. So that enabled us to get our different options with inversion or not inverted. So inversion. Okay, kind of fun. Fun thing to think in mind. Okay, so after doing some examples, let's learn. It's time to learn something new again. Oxidation. Remember our oxidizing scale? If we start off with one bond to oxygen and we add an oxidizing agent, we can get 2 bonds to oxygen to an aldehyde. So this is alcohol. This is aldehyde. Introduce another oxidizing agent, we can go to 3 bonds to oxygen and get a carboxylic acid. And if we overdo the oxidation, we break it off and just make lots of CO2. Usually CO2 is not the goal because we just destroyed it, right? Now, that's with a primary alcohol. What does it look like with a secondary alcohol? If we oxidize it, we get 2 bonds to oxygen instead of aldehyde. That's when we can get a ketone. We cannot arrive at the carboxylic acid without something particularly strong, but it's possible. So not in all cases will anything happen because we're done. We'd have to actually cleave that bond. So we'll mention that when that applies. So this is secondary. Now we can also add an extra strong oxidizing, like a one that bypasses the aldehyde and goes straight to carboxylic acid. So stronger oxidizing agent that will not destroy it, but won't stop at the aldehyde. So just some things to keep in mind. Let's see that general scheme. So this is kind of something I want you to keep in mind as we go through adding bonds to oxygen. Now we could of course go the reverse way with a reducing agent, and we will cover those eventually. But right now we're going to focus on what is the O in brackets that allows this transformation to happen. Okay, so we are going to see a family of molecules containing chromium. Nice and toxic. Here's the Lewis structure down here. Pyridinium, so protonated pyridine, hence the term pyridinium, the cation sort of phrase for it, right? Pyridinium. Chlorochromate is going to be abbreviated PCC. You may see those structures drawn. You may see PCC. I don't typically say memorize these structures and reproduce them out of thin air, but you want to recognize them. If you see those over the arrows, or you see the word over the arrow, you might see pyridinium chlorochromate, or you might see PCC. All three are interchangeable ways to write out that reagent, okay? So PCC is an oxidizing agent. It's one of the milder ones, like the black O in brackets. Okay, so what it does is it adds a bond to oxygen. And the mechanism for a lot of these transition metal ones, sometimes I'll show one step, but that's not in the scope of this class. It takes us on too many tangents, so I'm sorry to say we're not going to look at the mechanism for these chromates. But I hope conceptually you can envision how it's a source of oxygen. So see that high ratio of oxygens? That should remind you that it's an oxidizing agent. So in fact, I liked seeing the structure more than seeing the name, unless you could remember that chromate meant lots of oxygen, CrO3, right? So, so that is another clue. Okay, so PCC over the arrow, faster to write, of course, but conceptually remember that's a source of oxygen. And it's actually a mild oxidizing agent. It stops at the aldehyde. So let's label what we have here. Primary ROH stops at aldehyde. Why do I say stops? Because in that oxidizing scale I drew above, it could have kept going, could have kept oxidizing, but it doesn't. Other reagents will. So stronger than PCC is plain old chromate, also written as sort of like a dimer CR2O7, okay? And one of those two mixed with sulfuric acid and water or acidic water is the cocktail known as Jones reagent. So sometimes you will just see Jones over the arrow. That's what that means. This whole thing is Jones reagent. Okay, but you may also see the structures or the actual formulas written out. Jones reagent is stronger. It goes all the way from a primary alcohol to a carboxylic acid. Notice how the previous case we only added 2 bonds to oxygen, or add 1, increased it to 2 bonds to oxygen. Now we have 3 bonds to oxygen. So stronger oxidizing agent. You know, I'm just going to write as O in the brackets. Stronger O. This is a weaker O. I don't like to say weak because it does the job well, so I'm just going to call it a mild O, like mild salsa versus spicy salsa. This is the spicy oxidizing agent. This is the mild variety. So it stops at the aldehyde. So it depends on what you're in the mood for. You want a carboxylic acid, go for the spicy Jones spicy brand. They could brand that on the reagent bottle. Okay, so that's the story with, you have to worry about that with primary alcohols because look at their options. Those 2 H's can be replaced easily with either 1 bond to O, so only 1 H replaced, or both H's replaced with 2 bonds to O. Secondary alcohols don't have quite the same flexibility. That makes them easier to predict. So secondary alcohol means that we have either Jones or PCC. So e.g. Jones or PCC. Doesn't matter what you give it, it's going to only have space because there's only 1 H here, right? So let's draw that H. That H is gone now. And unless it cut off and cleaved in our group, which can happen in very extreme cases, but it's not strong enough to do that. So it makes sense that because there's only 1 H available, there's only 1 bond available to be made. So oxygen only was able to increase its bond to 2 bonds, from 1 bond to 2 bonds. So no matter what, you get a ketone, whether you use Jones or PCC. Not PCCC, like I wrote there. There we go. Ketone. Let's give it some color, actually. I started that in green, so I'll write that in green. Ketone. Secondary alcohols make ketones. Tertiary alcohols. No reaction, understandably, because there's no space to put that extra bond. Is that a tertiary alcohol? No. Fix your notes right now. R. Tertiary alcohol. 3 bonds to the alcohol is attached to a carbon with 3 other R groups. There's no degrees of freedom. No H to take off. So no reaction, also written as NR. Okay, so know the difference between what happens with primary, secondary, tertiary. Let's do that in some real examples for fun. Now, the more leveled up examples will have both mixed in. So that's what we'll practice now. So look at our alcohols. Is that primary or secondary? Well, that's attached to the carbon. The carbon it's attached to has 1 carbon, 2 carbons attached. So secondary. How about this one on the end? This O is attached to 1 carbon. That carbon is attached to only 1 carbon. The 1 carbon has only 1 carbon attached, so it is primary. So treat those accordingly. Assume you have excess, more than enough to react, unless it says otherwise, 1 equivalent or something like that. We take the secondary to the ketone, we take the primary to the aldehyde. Okay? How about this one? Same starting material. So we already know the designation, ketone. However, Jones is the spicy oxidizing reagent. So it's going to go all the way to the carboxylic acid. Jones again. But let's look at our starting materials different now. Secondary alcohol, tertiary alcohol. So what do we get? Ketone and no reaction. I hope that helps get you started. I want you to practice some more of those. Now, did I leave out a Grignard section? I did. I'm going to, you can either add a page if you feel like I'm getting too squished here, but I cannot not talk about the Grignard reaction. I meant to put that as a typed prompt in here. That's okay. We'll have one thing we write by hand right now. And if that's all we write, then we're doing good. So I'm starting a section called Grignard. Okay, so here's the overview of Grignard. It's a name reaction. It's a very important one at that. It really deserved a type section. I think I've taken turns moving it back and forth between 211 and 212, and I might have just, I should have just left it in instead of cut and paste. Because it's so important we cover it twice. And actually in your book, it's covered more than twice because it fits in the alcohol section. It also fits in the carbonyl section because look what I'm writing over the arrow, which is why I'm introducing it now, because we just learned how to make carbonyls. So this is how we can use a carbonyl, right? But we're going to use a carbonyl to make an alcohol, which is why it's in the alcohol chapter, because you make alcohols with it. You don't react the alcohol, but we know how to react to alcohol to get here. So kind of, you can see why it fits in both spots, but it's such a well-known reaction that it's often emphasized by covering it more than once. So you get to see it more than once. You'll know it really well by the end of Organic 2. So I'm going to show you what happened here. It's a little strange reagent. There's this magnesium halide attached to an R group. We have to make that, by the way. It's not just something that you can come by naturally. Throw in a ketone and work up with water, we get an alcohol. So ketone or aldehyde, like what we've just made, and we get an alcohol. But not just any alcohol. Let me point out what's happened. This R group, this R prime, is now attached to a carbon that had the ketone. That means we made a new carbon-carbon bond. Pausing for effect. That's a big deal. Until now, we've only made a carbon-carbon bond with acetylide. Acetylide gets old after a while in synthesis. It sometimes takes too many steps to get to what we need, especially if we wanted something that already had an alcohol when we're done. So if your goal synthetically is something with an alcohol and you need to add carbons, Grignard's going to be your other go-to. Just keep in mind that you have an alcohol in the product. As opposed to acetylide, you get that triple bond. So you kind of have to think about what would be more beneficial and efficient. So now I have two ways to make a CC bond. So that's another wow moment. I want this to stand out in your notes because you don't want to forget the Grignard. It is a little complicated looking thanks to that reagent. We have to make that reagent. So in order to make it, this is called the Grignard reagent. So in order to make it, reagent, you start with something very familiar. Rx, alkyl halide. And I'm going to call it R prime because that's what we were using, R prime X. So you just have to start with an alkyl halide, and we've learned all kinds of ways to make those, even from alcohols. You throw an elemental magnesium, Mg, you might even see the 0 written there to emphasize it's just like it's literally the metal magnesium. In the lab, we shave it down a little bit, sand it off so that it exposes the magnesium that has not reacted with the oxygen in the air, like we said, that oxygen just kind of attacks metals and oxidizes them, and then they're less reactive. So we kind of shave it off so it's freshly exposed and throw it in the flask, and you just have metal stirring the flask. That's this magnesium metal in our alkyl halide. Then it does this process called insertion. This is a organometallic term. I'm gonna call that insertion. No arrow pushing for it. I know it's a little odd. It was organometallic. That's a subfield of organic chemistry, organometallic chemistry. Those chemists that deal with metals bonded to carbon and those reactions therein. Grignard is part of that. I'll write that down here. Organometallic. Those organometallic chemists have their own types of mechanisms and terms, and we get a glimpse into it because, you know, this is a survey course. We get to dip our hands into all the different types. It's not just the bread and butter, but this is an idea of what happens with organometallic chemistry. The arrow pushing is not illustrated. You get, for this step at least, they just write a word insertion where it actually inserts itself, increases its oxidation state. So now we have 2 bonds to it. Why do we do this step? Magnesium is a metal. Therefore, it is delta plus. It's got a low electronegativity. And yes, the halide is going to be high electronegativity, but what does that do to carbon? It's a lower electronegativity than carbon, creates a dipole here that makes carbon nucleophilic. This is our Grignard reagent. The beauty of it is carbon is now nucleophilic. It's ready to attack and make a bond. What do we need to do this attack? We take our homemade Grignard reagent, and we throw in, so now we have a delta minus here, delta plus. That bond is more polarized, ready to break. We throw in our, let's put an aldehyde this time, but it could also be a ketone, so I'll put that in parentheses, that either one's possible. We throw that in, and the bond between R and magnesium breaks as it attacks the delta plus on the carbonyl. Open. R, and we have a tetrahedral intermediate with our R prime. The magnesium is not there anymore, or at least not in the substrate. Whether we had a ketone or aldehyde depends on whether we have an R or H there. Our O is opened to an O minus. That's why we need the step 2 for the workup. That's step 2. The water is there for that purpose. So since I'm showing the mechanism, I'll show even this step, but we all know that that's a simple proton transfer. And we have increased our carbon count. We've also gotten rid of our pi bond. So if those are things you desire to do in a synthesis, it could be very useful. Grignard reaction. It'll come back. We'll do more of that. Okay, so now that we have made alcohols and we have reacted alcohols, we're going to look at a special category called diols. I'll pause here, actually. Go practice some Grignard. That deserves more attention. We'll come back and do the diols. That shifts gears enough.